5. Magnetic braking with Faraday. For an introduction to this lab, the purpose will be to collect observational data of a magnet falling through a conductive tube of aluminum foil. We will model the magnet and tube interaction computationally, and then compare the computational predictions with the observed data. Key concepts in this lab are Faraday's law, the Biot-Savart law, and Newton's second and third laws. These are pictured to the right. For the results, the experimental value was 1.246 seconds, and the computational value was 1.15 seconds. Systems and surroundings. We used a magnet to model a magnetic dipole with aluminum foil, modeling the tube through which it fell. The surroundings would include the magnetic field of the polarized magnet pictured to the left. The system is the aluminum tube and the magnet, while the surroundings would be every other force acting on the system. Assumptions are air resistance on the falling magnet is negligible, and gravity on the magnetic force from the aluminum tube are the only forces acting on the falling magnet. The procedure is as follows. We first marked the end pole on the bar magnet, then positioned our tube as we needed to record with our phone to get the timestamps. Measurements and data. The measurements are seen on the left and the trials in the table on the right, where the average was 1.246 seconds. Why can't we just use a ferrous tube, for example, a steel pipe? Because the ferrous tube contains iron, and iron contains magnetic properties, so if a magnetic field from the iron had been induced, it would interfere with the magnet, thus skewing the data. What happens to the magnet? How does this compare to the magnet falling in free space without a tube? The magnet falls through the magnetic tube slower than it would in free space, as there is an upward magnetic force acting on it due to the induced current in the aluminum tube. This is the glow script model. This is where we first initialize the graph. And then this is step 1, and this is step 1, the second part, where we set the initial conditions. Step 2, where we made the magnetic field function. And then step 3, where we made the magnetic flux function. This is the simulation loop, which was a motion depiction and visualization of the loop. We let the magnet drop instead of stopping at -L, and then we controlled how fast the simulation ran. Larger numbers would run faster. This is where we calculated the magnetic force from the tube on the magnet, and also step 7 and step 8, where we plotted a graph of velocity versus time for the magnetic force as it dropped. This was the velocity versus time graph at the end of the run, and we had the tube created, and the time in tube was 1.168 seconds. So the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. What color corresponds to clockwise current as viewed from above, and which counterclockwise? Blue corresponds to clockwise and red corresponds to counterclockwise. This can be known using Lenz's law. What happens to the dynamics of the system when you flip the magnet around? The direction of the current would flip and the magnet would still fall through the tube. How does the total time in tube of your real world system compare to that of your computational system? How might this be made more accurate? Both values were fairly similar. When the adjusted mu value was used, the computational model could be made more accurate by splitting the tube into more rings, or by reevaluating the magnetic dipole of the magnet and refining it through an experiment. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? At the beginning, the gravitational force and magnetic force was balanced. In the middle, they are equal to each other, and then at the end, they are once again unbalanced. Model discrepancies and sources of error. There were no model discrepancies, and sources of error in the experiment were most likely human errors, such as an incorrect value of mu being calculated in lab 3. And lastly, further discussion questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Due to Ohm's law, the current in the aluminum tube would be much greater, thus creating a much greater magnetic force. This could also possibly make the magnetic force greater than the gravitational force, causing the magnet to not fall at all. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? The induced current in the tube would likely be less, as the holes would disrupt the current, and the magnet would also likely fall quicker due to a less strong upward magnetic force.